Hello everyone, today we are going to talk about functionals and functional derivatives. So at first I am going to tell you what is a functional. So I am hoping that you guys already know what a function is, but still I am going to just introduce them. So basically a function is a machine where if you input a number, it will give another number as an output. Okay, so that is a function. For example, f of x equals x squared is a function. If you input x equal to 2, it will give out f of x equal to 2 squared, that is 4. So this is a function. And a functional is another type of machine where it will still give the output as a number, but here the input is not a number anymore, it is a function itself. So yeah, functional is a machine where if you give a function as the input, it will give out a number as output. And I will be giving some examples. Let me just erase the first part. So the first example of a functional, we denote functional using capital letters, and within square bracket we denote the function which we are using as the input. So yeah, so the first example is this one. Okay, so this is an example of a functional. If you give an input such that if you give f of x equals x squared as input here, then it will give an output equals this thing. And this is, if you know integration, then you will easily get this thing. This is nothing but 1 over 3. Okay, so let me just erase this thing. Another example is another functional g of f. This is also an integral. Okay, so this is another example of a functional, and if you input x squared this time, then the output will be integration minus a to a 5 times x squared to the power 2, that is x to the power 4 dx, that will be x to the power 5 with limits minus a to plus a, and it will give out 2a to the power 5. So yeah, this is another example of a functional, and I will be giving you another example where I will show you that we have the trick or the freedom to write any function as a functional. Okay, so I will erase this after 1 or 2 seconds. Yeah. Okay, so I'm using another color this time. The third example, it tells you about a function. This is how I write the word function. Can be thought of as a trivial functional. And how can it be thought of like that? Okay, so if we have a function f of x, we can think this using the delta functions. So this is a valid equation, right? And if you are familiar with the delta functions, if not, then I highly encourage you to look about delta functions in some of your textbooks or in the internet, because we are going to use a lot of delta functions today. And this is, if you can recall, this is nothing but a functional, and we can say this is a functional of f with x. So I am denoting this is just a notation, nothing else. Okay, so yeah, so this is how we can write any function as a trivial functional using delta functions. Okay, so when we input some function f in this functional, that is this thing, then it will give the output of f of x at some point x, right? So yeah, okay. Now, as we have enough idea about functionals, we will be looking into functional derivatives. So let me just erase this thing. So now we will be looking into functional derivatives. So before we write the fundamental definition of a functional derivative, I would like you to recall the ordinary derivative of a function. Recall that if a function is f of x, then derivative of f of x with respect to x, or d dx of x, this will be equal to limit epsilon goes to 0. Epsilon is a very small a quantity, a number that can be added with x, f of x plus epsilon minus f of x divided by epsilon. I hope you all have taken a class of calculus and you know about this definition. This is a very fundamental definition that if you cannot recall, then you can look it up in high school textbooks, in mathematics textbooks, or you can also look it up in the internet. So yeah, so this tells you how the number returned by this function changes if I slightly change x. Okay, so yeah, so how the output changes if I slightly change the input. That is what derivatives are. Okay, so now for a functional, similarly, a functional derivative of some functional f, capital F of small f, is, so in this part we have seen that a derivative is nothing but observing or analyzing how the output changes if we slightly change the input, right? So in this context, it is how the output number changes if we slightly change the input number. So now a functional, it still gives a number as an output, but the input is now, oh, excuse me. So for a functional, the output now is still a number, but the input is a function now. So the same, using the same context, I can say that a functional derivative tells you how the output number given by this functional changes if we slightly change the input function small f. Okay, the same thing. But now the definition, in the definition we won't be using this sign d of dx, d over dx. We will be using a slightly curly delta, this thing. The definition is same as follows. Here I have used x prime and x to distinguish the derivative and the variable that is inside the functional. So x is the point at which I am finding out the derivative, and x prime is the variable that is in the functional or the expression of the functional. So as we cannot just simply add epsilon to f of x prime, that will globally increase the value of f of x prime by some small value epsilon. So we want to increase the value of f of x prime at the particular value of x. So that's why we have used a delta function which is 0 at all the places where x prime is not x, and it's undefined at x when x prime is equal to x. But when we have seen previously in the examples that a functional is trivially a definite integral. So a delta function inside an integral is not undefined. So we do not have to worry about the undefined part of the delta functions. Okay, so this is how functional derivative is defined, and this obviously, as I have told you before, I'm mentioning it once again. It tells you how the output number given by the functional capital F changes if we slightly change the function small f. Okay, yeah. So now we are going to look at some examples. So before that, I am going to erase this. Okay, so the very first example, it's a very simple functional I of f equal to this thing. Okay, let me just change the ink once again. I think this will be, yeah, this will be fine. So it's a little faded, so I'm going to write once again. So this is a functional I, capital I, of small f, and we want to find the functional derivative of this functional, and this will be like this. So the variable here is x, and we are finding the functional derivative at some point, suppose x naught. Okay, so the definition, according to the definition, I'm going to write down the expression. Okay. Yeah. So now you can clearly see that this part is cancelled out by this one. So we can write this is equal to as epsilon is not related to x, we can simply take it out of the integral, and this will exactly cancel out the epsilon in the denominator. So this will be equal to this thing. And if you recall the properties of delta functions, then you can understand this, that this will be equal to 1 when x naught is in between, some place in between -1 and 1. So when x naught is in between -1 and 1 and 0 otherwise. Okay, so this is the very first functional derivative that you have seen, perhaps. If you have seen the functional derivatives before, then it is obviously not the first one. But yeah, so this is how we differentiate a functional with respect to a function. Okay, so now I am going to give you another example. So I will erase this one first. The second example, another functional j with some limits Okay, so there are some limits here. I'm not writing it. I have to write the limits again and again. So that is why I'm not writing any limit, but it does not mean that it's an indefinite integral. It's a definite integral. I have just omitted the limits. So there are limits in this integral. Okay, so using the same definition, we are going to calculate the functional derivative of j. Okay, so this will be equal to I'm just writing the expression according to the definition. This thing. Now, this part is what we need to worry about. What we will do here, as epsilon is very small, because we have taken a limit epsilon tends to 0, we can Taylor expand this thing, or if you know binomial expansion, that's the same thing. It will give me a beautiful structure, that is f of x to the power p plus p times f of x to the power p minus 1 times epsilon into delta y minus x. And there will be other terms as well, but in those other terms there will be the terms will include epsilon square, epsilon cubed up until epsilon to the power p. But as we have taken epsilon to be very close to 0, we can omit these terms. As a number that is very close to 0, the higher power of that number is even closer and can be approximated to be equal to 0. So we will neglect these terms, and so this is the Taylor expansion of this part up to first order. Okay, so yeah, okay, minus, okay, I have forgotten a third bracket here. Okay, this thing. Okay, so now you can see that we can simply integrate f of x to the power p times phi of y dy, and this term plus this term, integrating this term, then subtracting this term, which will be exactly equal to the first part of this first integral. Okay, so then we will have this term and this will exactly cancel out each other. Then we will have, sorry, we will have this term only, which will survive from after this line. Okay, so I'm going to erase the first line here. you can clearly see that this epsilon can be taken out of the integral, which will exactly cancel out this 1 over epsilon, and then we will have the answer. So let me just erase this part, the first two lines. So this will be exactly equal to integral of this thing. Okay. Oh, so I have written y minus x here. Okay, so it doesn't matter. Okay. So again, from the properties of delta functions, assuming that x is inside the limit of this integral, we will have the answer this thing. Yeah. Two more examples. So now we are going to do a third one. I'm just erasing this part. Another functional h of f, which is this thing. This is a functional of f which is inside another function g, and yeah, then we have taken the integral with respect to x. Yeah. So using the same definition, we will find out the functional derivative at x equals x naught or x0, whatever you are comfortable with. This will be equal to this thing. Okay. Now we will do the exact same thing as we did in the last example. We will Taylor expand this term and we will get this thing. Once again, we have neglected the higher order terms as epsilon is very small here. So here g prime is nothing but this thing. Okay. Okay, so now you can clearly see once again that this part will exactly cancel out with the second part, and we will be with this part only, And once again, we can take out the epsilon out of the integral and it will cancel out this part and we will get the answer this thing, which will be exactly equal to this part. Yeah. We will do another example, the last one, and after that we will have enough introduction about functional derivative to continue to the next topics that I am planning to record. Okay, so I'm gonna erase this part. So now we are going to do the last example. I'm gonna change the color. We will find out the functional derivative of this thing. Okay. I'm writing d dy of f as f prime. Yeah. So now, okay, let me just put a partial derivative on, because it doesn't matter if it's a function of y, so it's the partial or total derivative, it doesn't matter, it will give the same answer. So now this thing will be equal to, using the same expression, I'm going to write here I am going to consider this first integral. This one will be dy, integral dy of g of, if we act del del y on this part, then it will give f prime plus epsilon times delta prime of y minus x. So delta prime is the differentiation of delta y minus x with respect to y, and as we will see that this part, this term will not give any problems, as we will be doing a trick, or we will be doing the mathematics in such a way that the derivative here cancels out. Okay, so now using the same method we will Taylor expand this, and this will give so here g prime is, okay, let me just write it down like this. Yeah, and I'm omitting and I'm neglecting the higher order terms as epsilon is very small. Yeah, so you can see that this term will exactly cancel out this term. So we will be left with only this part. Okay, so I am going to erase this thing and I am going to write this part only. And similarly, we can now take out epsilon out of the integral and it will cancel out the 1 over epsilon part, and this will give us this thing. Okay. Now what to do? Now we will do an integration by parts like this. We will take this thing out, then we will multiply this with the integral of delta prime, that is delta y minus x, minus, and this is at limits a and b, minus integral from a to b dy dy of dg of f prime df prime times integral of this part, that is once again this thing. So as I have told you before, we did integration by parts so that we can omit the problem with delta prime. Here there are no delta primes now, so we are good to go. Now in this part, x is in between a and b, not equal to them. For that part only, if x is in between a and b but not equal to them, putting b here and a here will both give 0, because delta of something minus something will give 0 if they are not equal. So this part will be 0. So we are left with that part. So that part, using the same property of delta functions, we can write that this will be equal to d dx of this thing. So this will be the answer. Okay, so that's all for today. I will be recording another class on some further topics that is related to functional derivatives. That's why I recorded this one first. So yeah, so bye for now.